Equations of motion. To describe and represent the motion of objects, there are 5 equations that can be used. This video will help explain each equation and how they can be found. There are 6 variables used in these equations. They are delta v, which is the change in velocity, delta t, which is the change in time, acceleration, with a, which stands for acceleration, v2, which stands for final velocity, v1, which stands for initial velocity, and lastly, delta d, which stands for displacement. To begin, to aid us in deriving the equation, we take a look at a velocity versus time graph. The slope of the line on the graph shows the change in velocity over time, meaning that the slope is equal to meters per second or meters per second squared, which happens to be the units for acceleration. From this we can conclude that acceleration is equal to the change in velocity over the change in time. To find our first equation, we start off with the acceleration for slope, as in a equals delta v over delta t. The change in velocity can be substituted by the final velocity subtracted by the initial velocity. This means that a equals v2 minus v1 all over delta t. Our next step is to isolate for final velocity, or v2. To do this, we want to multiply both sides by delta t, which gives us a times delta t equals v2 minus v1. Finally, we move v1 to the opposite side in order to get v2 by itself. The final equation that can be used when finding the final velocity is v2 equals v1 plus acceleration times delta t. An example of how to use this first equation is a hockey player accelerates from a velocity at 6.2 meters per second east to 8.8 meters per second east in 1.6 seconds. Find the hockey player's acceleration. To begin, we want to list all the knowns and unknowns. To find a, we use the equation that we just discussed. First off, we need to arrange the equation and isolate for a. To do this, v1 needs to be moved to the other side and be subtracted from v2. Next, delta t gets divided from a, and we know that what you do to one side you must do to the other. So our final equation is a equals v2 minus v1 divided by delta t. From here, we sub in our givens and solve for a. After some calculation, the acceleration of the hockey player is found to be 1.625 meters per second squared. Let's not forget about significant digits. The final answer is 1.62 meters per second squared east. And remember that acceleration is a vector and that it needs a direction. Our second equation of motion is one of the formulas used to find the displacement. Referring back to the velocity versus time graph, the graph represents the area underneath the line. To create the formula for delta d, we split this area up into 2 parts: a rectangle and a triangle. Both of these shapes are fairly simple, and we know how to find the area of each: length times width and base times height divided by 2. So the area under the graph equals length times width plus base times height divided by 2. Knowing this, we can sub in our graph variables into the equation to get v1 times delta t plus delta t times v2 minus v1 all over 2. To simplify this formula, we can sub in a delta t in place of v2 minus v1, because as we stated in the previous formula, they both equal the change in velocity. Once the variables are collected, the final formula is delta d equals v1 times delta t plus half of a times delta t squared. The third kinematic equation is very similar to the second, as it is again used to find the displacement of the area underneath the line. This time, instead of adding, we subtract the triangular shape made in the dotted line by having a larger rectangle. The equation that we will end up with is delta d equals v2 times delta t minus delta t times v2 minus v1 all over 2. As shown in the last formula, a times delta t is subbed in for v2 minus v1, and like variables are collected. Concluding, the formula equals delta d equals v2 times delta t minus 1/2 of a times delta t squared. These equations can also be shown in an example. A car is traveling 25.0 meters per second east. A driver notices a bunny 100 meters in front of the car and slams on the brake, slowing down at 3.6 meters per second squared west. Does the car stop in time if it takes 5.9 seconds to stop? Remember to list your knowns and your unknowns and to create a reference frame. For this problem, we will use the positive equation because we were given the initial velocity rather than the final velocity. From here, we sub in our givens and get 84.8 meters east as our answer, after significant digits are put into consideration. 84.8 meters is less than 100 meters, and so yes, the car does stop in time. We create our fourth equation differently, but is again used to solve for displacement. To begin, velocity is measured in meters per second, and that is measured by displacement over time. One can also find that velocity is equal to v1 plus v2 all over 2. This means that the two formulas are equal to each other and can be put together in one formula. So v1 plus v2 all over 2 is equal to delta d over delta t. Once rearranged to solve for displacement, this formula is delta d equals v1 plus v2 divided by 2 all times by delta t. Our fifth and final kinematics equation is actually derived from the equation in number 4. We start off by rearranging it so that t is on the other side, meaning that delta d over t is equal to v1 plus v2 over 2. Our next step is to multiply both sides by v2 minus v1. We are allowed to do this because both sides of the equation are being multiplied by the same. This makes the equation the same as left side equals right side. This gives us delta d over delta t times v2 minus v1, which is equal to v1 plus v2 all over 2 times v2 minus v1. From here we can sub in delta v for v2 minus v1 on the left side of the equation, because that eventually leads us to having a times delta d. Remember that delta v over delta t is equal to a. Our next step is to isolate and expand the right side. We multiply both sides by 2, and if you notice that the right side is actually the factored form of a difference of squares equation, meaning that we can change it into v2 squared minus v1 squared. In the end, the fifth equation is v2 squared minus v1 squared is equal to 2 times a times delta d. For our last and final example in this video, we will show you how to use the fifth equation. A rock is dropped from a 29.4 meter cliff. The rock's initial velocity is 3.73 meters per second down. Find the rock's final velocity. And remember that acceleration due to gravity is 9.81 meters per second squared down. Don't forget to list your knowns and your unknowns as we said before. And the reference frame is up is negative and down is positive. To solve this problem, we have to first isolate for v2. To do this, we move negative v1 squared to the other side so that it becomes just v1 squared. Then we square root both sides to get the full equation. v2 equals the square root of v1 squared plus 2 times a times delta d. From here we sub in our variables and solve to get the answer 24.3 meters per second down. Therefore, the rock's final velocity is 24.3 meters per second down. And that's it! Now you know how to find and use all the equations of motion. Good luck!